In this introductory lecture, we'll talk about the field of language technology. We'll see what language technology is and how it's applied. We'll also see some methods used in language technology. And finally, I want to give you a small demonstration of how language technological methods can be used for deciphering encrypted text. So, a key question in language technology is, how can we make computers understand language? And this is actually a very tricky question because understanding can mean so many different things. Do we understand language if we can transcribe speech into text? Do we understand English if we translate English text into Russian? I'm not sure. I know computers can do both of these things and we'll learn how they do it, but I'm not sure they understand language the way humans do. So because this is such a difficult thing to define, we usually say that language technology aims to process language using computers. And language technology has three subfields. Speech technology, which processes spoken language. Natural language processing, which deals with text. And then we have a third subfield, computational linguistics. And it's not an engineering field like the other two, it is a science. And it is concerned with the question, what can computers tell us about human language? This picture is from an article that used methods from population genetics to model the ancestry of Austronesian languages. Let's look at each of these fields a bit closer. So speech technology applies methods from signal processing, phonetics, and statistics, and it has two central applications, namely speech recognition, which aims to process speech and often convert it into text, and speech synthesis, which in a sense solves the opposite task. It converts text into speech. And this guy in this picture is of course the late Stephen Hawking, who was pretty well known for his iconic speech synthesizer sound. And Hawking's examples demonstrates that the reason for why language technology is so awesome. It can enable people with disabilities to function better, even to work as physics professors at Cambridge. Let's look at the next major field in language technology. This is natural language processing, or NLP for short. And it's the field of engineering which deals with written natural language input. And this is an extremely important field nowadays because the internet is full of text data, and computers have traditionally been pretty bad at handling text. So that's the reason why NLP seems to be everywhere nowadays. Everybody knows Apple Siri and Google Translate and other similar applications for translation and question answering. Well, Siri of course also includes speech technology because it does speech recognition and synthesis. So NLP can sometimes be found in surprising contexts as well. It turns out that when we're thinking of a word, we actually silently and subconsciously verbalize it, and this is reflected in our facial muscles. So here we have a system which can transcribe the activations of our facial muscles into text. And it seems that the authors immediately found some nice applications for this. So they used it to cheat in a chess game. So the player would silently verbalize his opponent's move, and then the device would suggest a counter move guided by a chess program. Okay, so these were engineering fields, but we can also use techniques in language technology for deriving linguistic information. This is an example from a paper from 2015. The authors used a technique called word embeddings, which are based on word co-occurrences in large text corpora. The authors were able to map the change in word semantics throughout the 20th century. This image illustrates an example from the paper concerning the word gay. We can see that the word is semantically similar to cheerful or dapper in the early 20th century, and then gradually migrates toward the meaning homosexual in 2005. And maybe the turning point here occurs somewhere around 1975. Okay, so why is it difficult to make computers understand language? Well, if we want to understand language, we need to know something about words. And one problem is that there are so many different types of words. And this means that your application will encounter a lot of words that it doesn't know. And this is called data sparsity. So whereas we may have a fairly good idea of what this sentence might mean, Trump scuttles Iran nuclear pact but offers no plan for what comes next, our system actually might see something like this instead, because it doesn't know all of these intervening words. And it may have a very hard time piecing together the proper meaning of the sentence, as you can understand. So one of the challenges is that you need to be able to deal with these unknown words. Another problem is related to the ambiguous nature of language. So ambiguity is present at all levels of language. And here we have an example of so-called lexical ambiguity, or the ambiguity of words. The word bank can mean very different things in different contexts. It can be a financial institution or a river bank, or it can be a verb and mean something like rely on or accumulate. And our system needs to be able to guess what the correct meaning is. And we people do this seemingly effortlessly, but when we try to build a system which can do this, we find out that it's actually a very hard problem. And the field of language technology that deals with ambiguity of meaning is called word sense disambiguation. And we'll see more of that later. But as I said, this can be a very hard problem. So people often use knowledge about how things work in the real world to disambiguate the meaning. But this is typically very hard to convey to a computer. Then we have some difficulties related to the speech signal itself. So the speech signal doesn't actually include enough information on its own to decode it into characters and words. And this is because different phonemes are in fact frequently pronounced exactly the same. So how do people understand speech then? Well, psycholinguistics tells us that we're constantly predicting the next word when we're listening to someone speak. And the earlier conversation influences our guesses. As speech recognition systems actually do something similar, they model words and sentences and text in order to be able to recognize speech successfully. So, in summary, language technology processes language using computers, and it has three subfields: speech technology, natural language processing, and computational linguistics. And language technology is challenging, for example, because there are so many word types. Natural language expressions are ambiguous, and the speech signal doesn't contain enough information to decode speech into text. Okay, so let's talk a little bit about the methods that are applied in language technology. And let's start with so-called rule-based methods. And these directly apply linguistics to the language processing problem. So we implement algorithms that formalize linguistics in a way that a computer can understand. And these have been especially successful in applications involving phonology, morphology, and orthography. And in general, they're useful when we're working in fields of linguistics that we understand well. So let's look at an example of a rule-based method. This is a little toy example of an inflecting dictionary. And unlike an ordinary dictionary, you can look up inflected word forms in an inflecting dictionary, as well as base forms. So this is very useful for people who are learning languages with rich morphology like Finnish, because they can look up word forms even if they don't know what the base form of the word is. But these inflected forms don't need to be fed into the dictionary one at a time. Instead, the dictionary uses a series of rules to derive the inflected forms based on base forms. And this makes it substantially easier to build these dictionaries. So let's start with the base form easy from the adjective lexicon. So currently we just have the base form. We can add a degree ending from a comparation lexicon. So as you know in English, we form the comparative by gluing an ending er onto the word stem. So let's take the comparative suffix. And now we have a base form, easy, a suffix er, and those are separated by a plus sign, which shows you the boundary between the word stem and the suffix. And that's called a morpheme boundary. Well, we know that easier isn't actually spelled like this because English spelling has its rule, but the stem final Y becomes an I in this context. So we can apply a rewrite rule that does just that. We recognize that we have context Y, morpheme boundary, and the following E, and our rule says that in this case we need to replace the Y with an I. And that's what we do. And then we have another rule which removes the morpheme boundary symbol, and we apply that rule and we get the result, which is the correct word form, easier. Now, as I said, this type of dictionary is very useful for language learners. It can also be extremely useful in systems which process languages with rich morphology, such as Finnish, because they allow us to analyze many unknown word forms into known base forms, which can help with that data sparsity problem we saw earlier. Then we have the other side of the coin, that is data-driven methods or machine learning methods. And here we apply statistics and mathematics to learn models which can perform tasks based on training examples. And these are quite strong in tasks like syntax and semantics, where we don't have a good idea about how the linguistics actually works, and where people more often break the rules, so to say. So data-driven methods are strong when we know how to solve a task, but it's difficult for us to formalize that knowledge. For example, we have amazing human translators, but they're not good at explaining how exactly they translate in a way which we could then convey to a computer. Let's look at an example of a data-driven system. This system predicts the scores people give to movies based on the reviews they write. So the idea is that we feed in a lot of these starred movie reviews as training data and learn a model based on those reviews. And this task is often called sentiment analysis. We're trying to judge whether people are happy or unhappy with the movie based on what they write. So a sentiment analysis model could be based on looking at words that occur in these reviews and learning that some of them, like intelligent and moving, are positive and predict a high score, whereas others, like boring, are negative and predict a low score for the movie. So then the idea is that after learning this model, we can feed in movie reviews without scores, and our system will predict the score for the review just by looking at the words that occur in it. So maybe it finds these words that it thinks are contributing to the score. And maybe it starts with a guess that the average movie should get approximately 2.5 stars. This is an initial guess, of course. So we look at the first word, brutal, here, which the system deems negative, so the score drops to 1.5. And we see that the next word, difficult, is again a negative word, so the score drops a little bit more. But then when we see well done, which is hugely positive, the system is prepared to disregard much of the earlier content. And maybe the second mention of brutal will have far less impact than the first one, so the score only drops a little bit. And the result is that we predict 4 stars for this review. Well, this is a very simple model because it only looks at individual words. There are other approaches to this type of tasks, and we'll look at those more later in this course. So I'd like to clarify something. There's a lot of talk about artificial intelligence in the media, and this is a term you almost never hear in NLP or language technology contexts. And that's because it's a very vague term. We use it to describe any system that exhibits intelligent behavior. Instead, you hear a lot about machine learning. And as we saw, this is the area of computer science that creates models that can learn to perform specific tasks based on training data. So, in summary, language technology uses rule-based and data-driven methods. And rule-based methods work well in applications where the linguistics is well understood. Whereas data-driven methods work well when we know how to solve a task, but we don't really know how to formalize our solution. And maybe they can also work well when we actually don't know how to solve the task. So let's look at the last topic of the lecture. And this is going to be a demonstration of methods in language technology for deciphering an encrypted message. And the previous tasks we saw word inflection, and sentiment analysis are tasks that people can do fairly well without thinking much about how to do them. So any Finnish speaker is able to inflect Finnish words, and any one of us is probably going to be able to recognize a 1-star movie review as a very bad review for the movie. In contrast, this deciphering task is a task that people can't do well at all, but a computer really excels at. And this makes it a really interesting task. So let's first start by looking at how to encrypt a message using a so-called substitution cipher. So a substitution cipher is a replacement table like this, and we substitute letters in our message by the relevant replacement. So for example, X here is replaced by a letter D. And if we have several X letters in the message, we'd always substitute with D. So let's do that substitution. And then we have a space, and that's replaced by C. So I'm marking the space with an underscore here. And then M is replaced by a G, and then we go on until the end of the message. And this result looks like total gibberish, right? It's very hard to guess what the original message would be based on this encrypted message. So we can formalize this type of a task using something called a noisy channel model. So we have some source, which in this case would be a human being writing a message. And then we have some noise source, which in our case corresponds to this replacement type table of the substitution cipher. And this substitutes letters with others and gives us this garbled up message. So our real task is to decipher these encoded messages. And in this setting, we don't have the replacement table. We only have an encoded message, and our task is to try to figure out what the original message was. So let's look at how we could do this at an intuitive level first. So when we start looking at character frequencies, we can see that the most frequent character in English actually happens to be a space. So it's a good guess that the most frequent character of this encrypted message might actually also be a space. Well, the most frequent character in this message is F, but we have two Fs next to each other at the end, so maybe that's actually something else. But the second most frequent character is C. So let's take a leap of faith here and assume that this is the space character. But I just want to point out, this is just a guess. The space might actually turn out to be something other than C. And this is a reason why this task is so incredibly difficult for people. We need to be able to entertain several hypotheses about what the space character might be simultaneously, and people are very bad at doing this. Okay, so we substitute C with a space. And then I'm going to give you two more correct substitutions just to make this task a little bit easier for us people. So we know that the colon is T and that F is actually S. We can look at this single character word here, Q, and since this is English, it's a good guess that this could be either A or I, because those are the most frequent single character words in English. And the first word starts with a T and ends with an S. So what could it be? Well, maybe this or thus or tons, probably this, right? And the dash looks like it could be a vowel since it precedes a T and a double S, and it can also follow a single S. And this type of information is actually information about the statistical nature of language. So for example, A is much more common than Z, which means that the probability of seeing an A in a message is bigger than the probability of seeing a Z. And C is much more likely to be followed by an A than a Q, for example. So an idea we'll look into more in later lectures is that we can formalize this kind of information in a statistical model called a language model, which includes information about the frequency of characters and also frequencies of character combinations. And this is what we are going to use for deciphering our encrypted message. So to be able to decipher, we want to model the source and the noise source so that we can go in the inverse direction from ciphered messages into plain text. And to model the source, we use a statistical language model, which we can compute simply based on plain English text. And it will tell us about the frequencies of characters and also about what kind of characters like to occur together. And we can't really model the cipher equally well. We know it is a substitution cipher, but we have no idea whether some ciphers might be more likely than others. So we'll just have to assume that all of them are going to be equally likely, basically. So this gives us a strategy for deciphering. We'll try out random ciphers and try to find a cipher that maximizes the probability of the deciphered message, given our language model. So let's look at how this works. I implemented a program called Decipher that does this. It tries out random ciphers, but it incrementally improves the cipher by replacing bad letter substitutions with better ones. And this is called Gibbs sampling, and we'll hear more about that in later courses. So let's start this thing. The number here tells you how many ciphers it has tried out. So currently it's tried out about 1,000 ciphers, and it's still looking pretty gibberishy. But when it gets the word space correct, then it starts to quite rapidly look more and more like English. So we actually already see a few words that are completely correct here. And it still takes a little bit of time for it to really get the entire message correct. But ultimately, at about 7,000 random ciphers, it has almost deciphered the entire message. There are some characters that seems to still be incorrect, but most of them are correct, and we can read the message now. So in conclusion, language technology processes language using computers, and it has 3 subfields: speech technology, natural language processing, and computational linguistics. And there are many challenges in language technology. For example, there are many different word types, and this leads to a problem with unknown words. Another problem is words and expressions are ambiguous. And the third one is that in speech processing, the speech signal doesn't contain enough information to decode it into phonemes and words. So to help with these problems, we can use a statistical language model which can capture information about the statistical nature of language. And this can help us, for example, decipher the encrypted text, but it can also drastically improve the quality of speech recognition and machine translation. Thank you.